What does this look like to you? What does it look like now? It's a cloud, yeah. It's a cloud. And sometimes when we have a cloud, sometimes it can develop a charge. Sometimes a negative charge on the bottom and a positive charge on the top. What would we call that, by the way, if it's neutral overall, but there's negatives on the bottom and positives on the top? Yeah, it's polarized, or we could call it a separation of charge. Yeah, either one. Now, what is that going to do to the Earth? The Earth that is neutral, equal number of positives and negatives. What's it going to do to the protons in the Earth? If we have the bottom of the cloud, we're focusing on the bottom of the cloud now because it's close to the Earth, right? The negatives on the bottom of the cloud are going to do what to the protons in the Earth there? Where are they going to cause the protons to go? Nowhere, right? It's a trick question. The protons are going to stay where they are. So what are they going to do, Emma, to the electrons? Yeah, it's going to cause those electrons to be pushed away. So these guys right here, not necessarily all of them, but lots of them are going to go down here. We're going to get, once again, a temporary separation of charge. What's that overall process called, by the way, when we get a temporary separation of charge? When we have charging going on without touching and without transferring charge, Chase? Yeah, we call that induction. That's all that's going on right now, right, is induction. We're creating a temporary separation of charge by induction because induction involves no touching and it involves no transfer of charge. And we haven't had either one of those yet. If this cloud and the ground have a big enough potential difference between them, you'll learn later on in the unit details of what potential difference means. But for now, it's just know that it's related to the energy. So if the cloud and the ground have a big enough energy difference between the two of them, then we can actually get electrons jumping or arcing from the cloud to the ground. Now, this tends to happen when it's damp outside more than when it's dry outside, right? You don't very often see lightning coming down to the ground on a dry summer day. Usually you see it when it's humid outside or raining outside, right? How come? Yeah, it's not that the energy difference is any bigger between the cloud and the ground on those humid or rainy days. It just means that it's an easier path for electrons to flow. So when electrons do flow, what do you call that? It's lightning. Yeah, it's lightning. Electrons are discharging from the bottom of this negatively charged cloud to the positive top of the Earth. It's lightning. It's arcing. It's discharging, whatever you want to call it. That process is now called what? Rather than induction, it's now called conduction. And it's called conduction because electrons are being transferred. We said that with induction, electrons are never being transferred. With conduction, electrons are always being transferred. We said with conduction, it usually involves touching as well. Is the cloud touching the ground here? No, it's not. So it doesn't always have to involve touching, but it does always have to involve a charge transfer. What's the top of the Earth going to become as a result of this conduction? Yep. Yeah, it's going to be charged negative because of the extra charges, the extra electrons from the cloud. So we've got charging by induction taking place before the lightning strikes, and then we've got charging by conduction taking place during and after the lightning strikes. Okay, I'm going to erase this for a second. Let's go back to when we have the cloud above the ground before the lightning actually strikes. You got a person standing here. That's either a really big person or a really low-lying cloud, one of the two, because it looks like it would only take about 3 of those people to reach the clouds. Regardless, it's been said, and I mean, I've never experienced this, and I hope that I never do, but it's been said by people that have been struck by lightning that just prior to being struck by lightning, they know it's going to happen. They know it's going to happen, but it's too late to do anything about it. How do you think they might know it's going to happen? Yeah, The hair, it tends to be the hair on their arms standing on end, right? It kind of feels ticklish on your arms because the hair on your arms starts standing on end. Can anybody suggest to me why the hair on somebody's arms might stand on end just prior to a lightning strike? Yeah, okay. Yeah. Basically, you get that separation of charge again, just like you did in the Earth. You get the separation of charge in the hairs in your arm. So what happens? They don't actually become negatively charged; they become positively charged, right? So if this is a single hair on my arm, magnified, and I had a bunch of positives and negatives, those electrons, those negatives, get pushed down to the bottom, leaving the hairs both positive charged. And then what happens as a result of this hair being positively charged and the hair next to it being positively charged? They repel each other. What's that called? Charging by conduction or induction? That's induction. That's induction because you're not transferring charge from the cloud to the person's arm, right? It's induction. There's no touching going on. We call it, specifically within induction, we call it a temporary separation of charge. Okay? And then when, of course, lightning strikes the person becomes negatively charged by conduction and also probably dead by conduction. Yeah.
I'm just curious, but if the person was already like saying negatively charged
Yep.
and all,
Yep.
would the lightning avoid the person?
That's a good question. If the person was already negatively charged, would the lightning avoid the person? Um, the answer to that would be no, because a person couldn't possibly have an amount of charge that was remotely close to the order of magnitude that the amount of charge that the cloud had. So as far as the cloud is concerned, the amount of charge that you have is really irrelevant. Okay? Even if you are negatively charged, it would really be irrelevant. Now, if you had enough charge, like enough negative, then yeah, I suppose it could repel the lightning bolt, right? But in practice, like you couldn't have anywhere close to enough negative charge to actually make that happen. Yep. No, I think he means like, you know, yeah, like that Van de Graaff generator over there has a negative charge on the ball with that Van de Graaff generator when we fire it up to 400,000 volts of potential difference. It's a lot of energy. Um, would it repel lightning? If I had that much charge on me, would I repel lightning? No, no, because even that Van de Graaff generator would have a lot of charge on it, but nowhere close to enough to actually repel that lightning. Okay, that's a good question though. Okay, good question. Yeah, it's just that there's effectively not enough because in the end you got this big fat Earth below you, right? And it is so massively neutral that any excess negatives that you have are just kind of an extension of that, which basically makes you and the Earth neutral effectively. That makes sense? Okay. Yep. Um, to make you pause. Well, not necessarily positively charged, but yeah, like we do put big metal rods on the top of buildings to attract lightning. They're called the lightning rods, right? We want to attract lightning to the top of buildings, but we don't make them positively charged. We just have them neutral, and we have them pointy because pointy things attract electricity, and we have them connected to the ground. So when the lightning strikes, we want to attract lightning there so that it strikes the lightning rod and then gets grounded, goes down into the ground, as opposed to striking something specifically on the building that will cause damage. So we attract it to that spot to avoid it hitting somewhere else. But basically the answer is yes, but we don't have to make it positively charged. Now, if you did make something massively positively charged, then yeah, it would attract lightning more. But just like making your body negatively charged and trying to repel lightning, it would take an unbelievable amount of positive charge to make any real difference there. Yeah, that's a good question. because there's a tremendous amount of energy in lightning. So if we could harness it, then that would be great, right? The problem is it's so unpredictable. And even when we have lightning rods, like it's pretty unpredictable when it's going to strike. So um, if you knew exactly, I would suggest that if you knew exactly when lightning was going to strike, more or less, when lightning was going to strike at least, then yeah, you probably could figure out a way to harness that. But because we don't, because it's so unpredictable, I don't think it's a practical thing to do. But there is a lot of energy, and it's electrical energy, which is what we probably want. But yeah, but remember to attract it. I mean, you can attract it by a lightning rod, but it's still rather unpredictable. Um, if you could attract it more by having this massive positive charge, you're right. But the amount of energy that it would take to make the massive positive charge would kind of defeat the purpose of attracting lightning, right? Good idea, though. All right, I'm going to give you something a little new here. It's just a bit of an extension of what we did yesterday. I'm going to describe for you a device called an electroscope. An electroscope is a device that detects charge. That's all. It doesn't tell us what kind of charge we have. It doesn't tell us how much charge we have. It just tells us whether we have charge or not. This is an electroscope. It's an electroscope that doesn't work particularly well, but we'll give it a little whirl here. You can see that it's essentially the same thing as we have drawn up on the board here. Okay, we see this metal ball at the top, or this metal knob at the top connected to a metal rod. And at the end of that, in this one, you can see these two little metallic balls, or two little metallic spheres on the end of it. Okay, we call them pith balls. Pith is material from the inside of a plant, and it's really, really light. And we coat it with this metallic coating. Why do you think we coat those pith balls with metallic coating? Like, what's the benefit of making them metal on the outside? Yeah.
To cause them to have a charge when if there is a difference, like.
To cause them to have a charge, yeah, kind of. To make them more conductive so that they can gain a charge. Yeah. Okay, we make it more conductive so that it's easier for charges to flow to or from them. Now this one over here, it's almost the same thing. We got this ball or knob at the top, this metal rod. This time, instead of having two spheres at the end of it, we've got these two really, really, really thin pieces of foil. It's like aluminum foil, like tin foil you have in your kitchen, except much, much thinner. Okay. You ever seen, you ever used gold leaf or gold foil for decorating, like baking? You ever seen that? You can buy it in the grocery store, actually, and it's actually gold. It's just incredibly thin. If you've ever seen it, we're kind of talking about something that thickness and that weight. Okay, much, much thinner than aluminum foil. All right, now what happens when I bring a charged object nearby this? Well, if I bring it nearby the real one that we have here, not much is going to happen. But we'll do it anyways and see if we can make it work this time. 1 out of every 10. I'm going to take this plastic golf tube. This is a tube that you put inside a golf bag to keep your clubs kind of organized. I'm going to rub it against this dead rabbit and make it charged. Okay, make the golf tube negatively charged and the dead rabbit positively charged. You can hear it discharging, actually. You hear that? Yeah, the electrons are discharging. That's how quickly it's building up the charge on the plastic golf tube. It's so quick that it's actually discharging before I'm finished charging it. When I bring this nearby, what you should see here, and you're probably not going to see it in this real electroscope, but what you should see is the pith balls in this electroscope should spread apart. Bring it nearby and use your imagination. See them in your imagination? Spreading apart? Look at that. That is so dramatic. That is so dramatic in your imagination. Those pith balls spreading apart right there. That's what's supposed to happen, is that they're supposed to spread apart. That's just a very, very poor quality electroscope, that's all. But why are they supposed to spread apart? Why? Well, look, this electroscope is neutral. It's got positives and negatives, though, all through it. Everywhere. But they're evenly distributed so that it's effectively a neutral ball on the top, a neutral rod, and then two neutral pith balls down on the bottom. It's neutral. But when I bring a charged rod nearby, let's make it a negatively charged rod nearby. Doesn't matter where I put it. Yeah, I can put it on the left side, the right side, above it, below it, whatever. Bring it near the knob or the ball of this electroscope. What happens? What happens to the protons? What happens, Emma, to the protons in this electroscope? They're not going to do anything. They're going to stay where they are, right? But the electrons are going to be repelled away. So these electrons that are up here start moving down here. Now, the two pith balls at the bottom of this both become negatively charged as a result of that, right? And if they're both negatively charged, what are they going to do? They're going to repel each other, and then they're going to spread apart. Does that make sense? If I take this negatively charged object away, what's going to happen? Well, they're going to go back to the way they were, and the electrons are going to scatter around randomly again, and those pith balls are going to come back together. Not because they're attracted together, but just because gravity is pulling them down. Yeah. I don't know, actually. Yeah, I don't know. I think it's not an electrical issue with it. It's a mechanical issue with it. I think like there's something sticky on it that's keeping them together, or the foil string, like the metallic string that's tying them to it, is like there's a lost connection or something there. I'm not exactly sure why it's not really working, but one of these days I'm gonna have to buy one that's better quality so that we can actually see it for real, but not just in our imagination. What's going to happen over here if I bring a positively charged object nearby? Well, once again, we get positives and negatives all throughout it. It's all neutral. What's going to happen to the protons in this electroscope over here when I bring the positive nearby? Nothing. Protons are going to stay where they are, right? What's going to happen to the electrons? They're going to get pulled up. So these guys are all going to go up. Well, not all of them, but lots of them are going to go up here. So you get the ball of the electroscope becoming negatively charged, but the leaves of the electroscope become positive. They spread out. So what happens here when I bring a negative nearby? Spreads out. What happens when I bring a positive nearby? Spreads out. It detects charge. If the leaves or the pith balls spread apart, we know we have charge. Don't know how much charge we have, but we know we have charge. Don't know what type of charge we have, because it happens. Same thing happens with positives and negative objects being brought nearby. Don't know what kind we have, but we know that we have charge. Now, what's going to happen if I introduce a ground wire here? It doesn't matter where I put the ground wire. These negatives that were pushed down into the leaves of the electroscope, they went to the leaves of the electroscope because they want to go as far away from this positive object as they can. The leaves of the electroscope are no longer as far away as they can go. So where do the electrons go now? Yeah, down into the earth. They don't go down into the leaves. They get pushed out of the leaves down into the earth. So what happens to the leaves now? What happens to the leaves? They go back together? No, they actually stay spread apart. But now they stay spread apart because they're positively charged. Make sense? The electrons were pushed down into the ground now. So the leaves are now positively charged. They'll still be spread apart. What happens when I take this away? They go back. Gravity pulls them back down together. What happens if I cut the ground wire and then take this thing away? Well, now the leaves are going to stay spread apart, right? Because they're positively charged and they have no way to go back to being neutral. Got it? Well, not forever, but they'll stay spread apart for a while. Eventually what's going to happen is the electrons will discharge from the air to those and then eventually neutralize them, because there are electrons in the air, right? But it's going to stay that way for a while at least. What happens if I introduce another ground wire? Okay, so the steps here, right? I put a negative nearby. It pushed the negatives down into the leaves. I grounded it. It pushed them out of the leaves into the ground. I cut the ground wire. I took the negative object away. Now I'm going to ground it again. What happens? The electrons come up from the ground and the leaves go back to normal, hanging straight down because they're neutral and gravity pulls them down. What happens over here in this one? Well, remember in this one, all the negatives were pulled up, so the leaves became positive. If I ground it, doesn't matter again where I put the ground wire, if I ground it, negatives are going to be pulled up from the ground. Now you got a whole bunch of extra negatives here. Well, eventually what's going to happen is they're going to start spreading out down here too. It's going to happen to the leaves. They're going to spread apart. Not because they're positive, because they're negative. Cut the ground wire, and they're going to stay that way for a while at least, because there's no way for the electrons to go back down into the ground. Yep. Cut it and then take away this. Yep. Yeah, there's more negatives all over the place than there is positives, so therefore the leaves would still stay spread apart. And it'd stay that way until you ground it again. You ground it by literally attaching your ground wire or by putting your finger on it, right? Because, I mean, if you're talking about something the size of an electroscope, you attach a wire down into the earth, all right, there's a way for electrons to come up or down. But if you touch it, like, as far as this is concerned, you're as good as the earth, right? Even if the electrons aren't going down through you into the earth, like, you're big enough to be the ground. You're big enough to be the earth. Okay, so even though you're not literally grounding it, it's we call it grounding it. Right? Make sense? All right. I got a few questions actually from your textbook that I want you to work on here. This is page 523, 7 to 10. I'm going to put them up on the board here, but you should also, of course, have chapter 10 downloaded from Google Classroom right now. Question number 7 relates to a picture from another page in the textbook. This is that picture. In this picture, we're using a negatively charged object to charge this thing positive. It becomes positive. Okay, we want to charge this sphere right here negative. So what would we do to make it negative by induction? Okay, make it the opposite charge by induction. Okay, number 8, 9, and 10 don't require the diagram. Give you a few minutes to work on those now. We'll take a look at 8 in a couple minutes, then 9. Or sorry, 7 in a couple minutes, then 8, then 9. Kind of one step at a time there.